In this example, we're going to use conservation of mass with our control volume tool that we discussed in the previous video to solve a fluid mechanic problem. We're given a bathtub that's 1/2 meter deep, 1.75 meters long, and 3/4 of a meter wide into and out of the board. And it's being filled through a faucet with an open valve at a mass flow rate of rho, the water density, times 2 meters cubed per hour, the volumetric flow rate. And we're asked to find the rate of change of water depth in the bathtub. So the very first thing we do, and you'll see me do this for all of the problems that we do in this class that are set up this way, is we want to draw our control volume. And what that does is allows us to dissect the problem and get a handle on what we need to do to solve it. So it's really analogous to the free body diagram that you used in statics. And your lecturer or professor in statics, I'm sure, stressed to you the importance of taking a step back when you start the problem and draw out the free body diagram. Well, here we're going to say the same thing. When you're trying to solve a fluid mechanic problem, the first thing you should do is take a step back, think about the problem, and draw your control volume. So let's do that. So in this case, I'm going to pick a control volume that follows the outline of the bathtub, like this, along the bottom, and then across the surface. Right, like that. So that's our control volume. And if you recall from our previous video, we're always going to define our unit normal vectors as being pointed perpendicular out, away from the control volume. So in this case, this top one is going to have a unit normal vector that's going to be positive upward like this. And that's the only one we need to worry about, because all the other surfaces of this particular control volume are solid boundaries, meaning that our v dot dA, no matter what, is going to be 0, so we can neglect those sides. Okay? So we have our control volume. Again, it's this volume inside the bathtub. And we have this unit normal vector pointing out like this. Like so. And the next thing we want to do is write out the conservation of mass equation for our control volume in its full form. And the reason we do this is that we can write it out in the full form, and then we can start looking at the control volume and then simplifying the equation as we work through it. So it's easiest to start with your control volume, then write out the equation you need to solve in its full form. So let's do that. So we're going to write out the conservation of mass equation in its full form. And that's going to look like d over dt times the integral over the control volume of rho dv plus the integral over the control surface of rho v dot dA. Okay, where again dA is equal to n hat dA. Okay, so that's our full form of our control volume, our conservation of mass, sorry. Okay, so now what we need to do is look at each of these terms. So the first term is d over dt times the integral over the control volume of the density times the differential volume. Well, in our control volume here, let's think about it. We've defined a fixed control volume, which is not changing, so that dv dt is 0. And because we're not given any information on the change of the density in time, we can assume that d rho dt is also 0. And 0 times 0 is 0. So now we can get rid of this entire term because we have and so basically what we're doing here is saying it's steady. Okay, so mass in equals mass out. All right, so let's look at the next term. Okay, the next term is the integral over the control surface of rho v, the velocity vector, dot dA. And as we mentioned earlier, all of the sides except for the surface, the top side of our control volume, that product is going to be 0. So the only one we need to worry about is the top surface. So across the top surface, we have a flow in of m dot n. So we say negative m n dot, because anything flow, because of the way our normal vector is defined, positive upwards, this is a negative flow, it's a negative flux into the control volume, plus, okay, now we need to think a little bit about the flux out. So the flux out of the control volume, well, we don't have any information on the spatial distribution of velocity, so we can assume that that velocity across that top surface, as it comes in, the water surface is going to rise. And that rising water surface is essentially an upward velocity. But since we have no spatial information on that variation, we can assume that that's a constant velocity. So we have v, and that v is going to look something like this. If we label this surface 1, so if this is surface 1, then we're going to have v1 is going to look like this, coming out of the control surface. All right, so we have rho, and we have v1. And because, again, don't have any information about the spatial variation in v1, then, and the area is fixed, we can say that this is simply times the area of 1, and our differential area is the entire bathtub surface. Okay, so now we've simplified that into rho v1a1, and that's going to equal 0. All right, so I didn't write this above, but we should have, that's 0. Okay, all right, so the next thing we need to do is think a little bit about what V1 means. So V1 is going to be equal to dH over dt. You see that? V1 is really the rate of the rise of that water surface. It's dH dt. That is our V1. So we can make that substitution. The second thing we can do is we can divide through by the density rho. So let's do that and write that out again. So the first thing we're going to do is divide by the density rho. The second thing we're going to do is substitute in dH dt for V1. And so that's going to look like this. Negative m dot n over rho plus dH over dt A1 is equal to 0. Okay. Then if we look at our definition of mn over rho, then that's a mass flux. If we divide the mass flux by rho, and you're even given m dot n as rho times a volumetric flow rate, this becomes negative q1 or qn plus dH over dt A1 is equal to 0, which, if we look at that, quickly becomes, oops, if we rearrange that, we get dH over dt is equal to qn over A1. We can plug in our numbers there. So we have 2 meters cubed per hour. We need to convert that into seconds, so we need to say 1 hour over 3,600 seconds. Divide that by our area, which is 1.75 meters times 0.75 meters, the length times the width, and we end up with 4 times 10 to the minus 4 meters per second. That doesn't have make a whole lot of intuitive sense to us, and so just to give you an example, that's about 2.5 centimeters per minute, or 1 inch per minute in English units. And so that's a pretty good flow into your bathtub. You'll fill your bathtub in 15 or so minutes in that case. So that's pretty standard, and that's how we could apply control volume analysis to solve this problem. Before we wrap up today, I want to take a look at a different way of doing this problem. So let's now define our control volume as one that expands with the water surface. So now we have it basically start with the same control volume, but now we're going to say that that control volume is going to expand with the water surface. So what happens is if we write out our equation again, so we have d over dt of integral over the control volume of rho dv plus integral over the control surface of rho v dot dA equal to 0. So we're going to do this. Again, we're doing the same problem. We're just going to take a slightly different definition of what the control volume is. So now if we say that the density is homogeneous and not changing because we're given no information on that, then we can pull the rho out of both the integral and the derivative. So we're just going to look at this first term here. This one right here. And what we're going to say is we're going to pull rho out. And you're going to get rho d over dt of the integral over the control volume of dv. Well, this integral here, right here, is simply the volume. So now we can rewrite that again as rho dv over dt, right? So we took that integral. The integral of dv is just the volume, so we have rho dv dt. And now let's think about what the volume is. So this volume that we've defined is going to be v, this volume, is equal to the area, that's the 1.75 meters times the 0.75 meters, times the water depth h, right? Well, the area here, this area, that's constant in time, so we can pull that out. So let's write that out again. So then we have d over dt, rho d over dt of AH. We can pull the A out, and we end up with rho A dH over dt. Now we can plug that back into our original equation, and we end up with rho A dH over dt for the volume side, the storage side, the change in storage. And then we have our fluxes. Well, the only flux in this case is m dot n. So we have minus m n dot equals 0. And then finally we end up with dH over dt, doing the same rearranging we did before, equals qn over A. Same answer. Right? So the reason we did this both ways was to illustrate the value of the fact that we are in control of the control volume. And we can define it any way we can. And there's good choices for the control volume, and there's bad choices for the control volume. So whenever you do these fluid mechanics problems, the thing to remember is when you start the problem, think very carefully about how you're going to define your control volume. It'll make your problem easier and probably give you a leg up in getting the right answer. Good luck.